In this section, we talk about implicit differentiation and related rates. So I've already done one video introducing implicit differentiation, so this is just doing one more example and writing it out a little bit so you can see the steps. So we use implicit differentiation when x and y are related by an equation. For example, if we have 3x squared plus y to the 7th equals 3x y to the 5th. So normally we're used to equations where we have y is some function of x, and then we just find dy dx by just taking the derivative. Nice and simple. But in this example, there's no way you're going to solve this to get y by itself. And so we need to find something else to do. But let's say, okay, we know that if we could solve it to get y by itself, then y would be some function of x. So what we're going to do is we do a hidden chain rule. We assume that y is a function of x, so anytime we take the derivative of y, we then have to multiply by dy dx, because we took the derivative of y, but there's also that inside function of x, so we have to times by dy dx. And then, so again, every time you take the derivative of y, you multiply by dy dx. And then when you've taken the derivative of everything, just solve to get dy dx by itself. So let's try this example. We want to find dy dx for 3x squared plus y to the 7th equals 3x y to the 5th. So you take the derivative of each piece just term by term like you normally would. So 3x squared, that would be 6x, plus. Now y to the 7th, that would be 7, y to the power 6. But wait, y was really a function of x. We just didn't know that, so we have to times on dy dx. Equals, now do this piece. This is 3x y to the 5th. This is actually going to be a little more complicated. We need to use the product rule. Which tells us the derivative of f times g is equal to f times g prime plus g times f prime. So again, right here we have a 3x times y to the 5th, so we have to use the product rule. So for this, let's say f equals 3x and g equals y to the 5th. Okay, so f times g gives us 3x, sorry, f times g prime. So g prime, take the derivative of g, so this would be 5 y to the 4th. But anytime you take the derivative of the y in it, you have to tack on dy dx. Plus now you take g, or y to the 5th, times f prime, which is just 3. Okay, so we've taken all the derivative, but our goal was to find dy dx. So now you just rearrange and solve for dy dx. As you're rearranging, you always get everything with dy dx on one side. Okay, so the trick to solve for dy dx is get everything with dy dx on one side and everything else on the other side, of course. So we'll have 7y to the 6th dy dx. Let's see, minus this whole 3x times 5y to the 4th dy dx equals, and let's see, we'll have a negative 6x plus 3y to the 5th. You factor out a dy dx. So I'll have 7y to the 6th. I'm going to simplify this to negative 15 xy to the 4th equals negative 6x plus 3y to the 5th. Oops. And we ran out of room here. And then you divide by everything that is in that dy dx. So we'll have negative 6x plus 3y to the 5th over 7y to the 6th minus 15x y to the 4th. And at this point, we're left with some x's and y's, but that's okay because it was too difficult to get y by itself, so we don't actually have to plug in the x's wherever we see y. So that's how you get dy dx. Now sometimes, or our equation could have represented a curve or some kind of graph, and so we might want to know, well, what was our slope of the tangent line? Slope of a tangent line just means find dy dx. So we found dy dx, and now we want to evaluate, or we want to plug in our points. But notice how there's an x and y, so you actually need to plug in the points x and y. So we're going to plug in x equals 5, and we're also going to plug in y equals 3.86. So you put those in everywhere you see x's and y's up above. So this, and so again, big line just means plug these numbers in. So this is going to be negative 6 times 5 plus 3 times 3.86 to the fifth over 7 times 3.86 to the sixth minus 15 times 5 times 3.86 to the power of 4. And I didn't double check, so hopefully I did it correctly the first time, so 0.09778. So this is pretty cool. This is our actual slope at the point 5, 3.86. So even though we couldn't find the equation of y equals to easily graph it, we can still tell you what the slope would be at that one point. Now related rates. Okay, so for related rates, this is very similar to implicit differentiation in that it's kind of doing a hidden implicit differentiation. So for related rates, we have an equation with two variables that are both responding to an underlying third variable such as time. And we say that each of these variables will then be a function of time. So x is going to be some function of time. We don't know what it is. And y is also some function of time. Again, we don't know what that actual function is. We just know that they're both responding to time somehow. So then we take the derivative like normal, but there's going to be a hidden chain rule. And what this means is every time we take the derivative of x, because x is a function of t, we have to multiply by dx dt, just like when we do implicit differentiation. And if we take the derivative of y, well, y is really a function of t, so we have to multiply by dy dt, etc. So whatever variable you're doing, you multiply it by d, whatever the variable is, over dt. So let's try examples. These are always going to be very application-based examples. So let's see, the volume of a spherical cancer tumor is volume equals 4/3 pi r cubed, where r is the radius of the tumor. The doctor estimates that the tumor is growing at a rate of 0.2 millimeters per day. The tumor is currently at 5 millimeters. How fast is the volume of the tumor growing? So when you read these problems, you're like, okay, so it's telling me something's changing at a rate, and then it's asking me how fast something else is changing. So it kind of sounds like multiple rates, because we're asking for a rate, and this is also a rate, and so we have multiple rates. Anytime you see something with multiple rates, you know it's related rates, and this is what you're going to do. Okay, so we start with our equation. We have this equation, volume equals 4/3 pi r cubed. And you start by taking the derivative. But when I take the derivative of v, the derivative of v would be 1. But I have to tack on dv dt, because volume is changing based on time, and radius is also changing based on time. Okay, and then this 4/3 times pi. Pi is just a number, not a variable. And r cubed would be 3r squared. But r, or our radius, is also a function of time, so I need to multiply by dr dt. So when you do related rates, you take the derivative like normal, but every single variable gets tacked on a d over dt. And at this point, I'll usually kind of stop and come back and look at what it told me up above. Okay, he estimates the tumor is growing at a rate of 0.2 millimeters per day. Okay. Ooh, and I just said the tumor is growing, but it's kind of implied that this is the radius. So it's saying the radius is changing at a rate of related to time. So this is a dr dt. How fast is the radius changing with related to time? Is 0.2 millimeters per day. So that's the dr dt. The tumor is currently at 5 millimeters. So the radius is 5 millimeters. How fast is the volume of the tumor growing? So they're asking us to find dv dt. So come back through and plug in everything that you know, and let's see what we're left with. See if we found everything we need. So dv dt, that's what I'm looking for. 4/3 pi times 3 times r is 5 squared, and the r dt is 0.2. Oh, looks like we've done everything. We're just down to dv dt, which is 62.83. And let's see, this is volume, so this would be millimeters cubed per day. So if you know how fast the rate is changing, you can then find the related rate of how fast the volume is changing. In our next one, this might seem like a similar problem because we actually did it in the last section using the chain rule. You can actually do it here as well, and I think it's a little bit simpler to do with related rates. So the revenue equation for an MP3 player's revenue R equals 24x minus 0.003x squared, where x is the number of MP3 players produced and sold. Now you might read this and think, how is this going to be different than any other problem? So keep reading. When the company makes and sells 400 MP3 players a day, if the company decides to increase production by 50 players per day. So this is telling us this is a rate. And then it's asking how fast, and that's another rate. Anytime you see a problem where it's telling you a rate and it's asking another rate, you know it's going to be related rates. And then you set up your problem and do like we did up above. So you take your equation of R equals 24x minus 0.003 x squared. And you take the derivative like normal. So derivative of R would just be 1, but you have to tack on dr dt because revenue is some function of time. Okay, because it was asking how fast will revenue increase per day, so it's talking about revenue with respect to time, so you know you have to do a dt. Okay, and then this 24x, this would be 24, but you have to tack on dx dt minus 0.003 times 2x, and you have to tack on dx dt because our x is also changing per day. At this point, you could rearrange and solve, but I usually just kind of plug in numbers before I try and do that. It makes it simpler. So it tells us our company makes and sells 400 players a day. So that means X is currently 400. They want to increase production by 50 players per day. So that means X is going up. So that's dx dt is 50. And how fast will the revenue increase per day? That means we're trying to find dr dt. So let's plug everything in. Dr dt equals 24 times the x dt, which is 50, minus 0.003 times 2 times x, which is 400, times the x dt, which is 50. And I put this in my calculator earlier, and I got 1,080. So based on these results, we get $1,080 is how much the revenue will increase per day. So those were some simple problems where they gave me my equation. Sometimes, though, they won't give you the equation. You have to come up with it first. So let's see. We have an airplane is flying 400 feet per second at an altitude of 4,500 feet. And it flew directly over Jim. So I've drawn a little sketch here. Here's my person. The airplane was up 4,500 feet. The airplane is going this way. I just drew it this way. And so x would be the distance that the airplane has flown, and y would be the distance from Jim to the actual airplane. And this would be a right angle. So to find an equation relating x and y, you can use Pythagorean's theorem. Of a squared plus b squared equals c squared, where c is the longest side or the side opposite from the right angle. So we would have 4,500 squared plus x squared equals y squared. Let's see. And then it says the airplane has now flown 13,000 feet further. How fast is the distance from Jim to the airplane changing? And so it's asking us to find a derivative. And up above, it told us that we have an airplane flying at 400 feet per second. That's another rate. So we have a rate, and it's asking us to find another rate, so related rates. Let's write down everything that they've told us. The airplane flies at 400 feet per second. That's x, which is where the airplane is actually going. So dx dt equals 400 feet per second. Okay. And let's see, what else did they tell us? That's the altitude, but I don't think we're actually using that, except for to get my equation there. The airplane has flown 13,000 feet. So that's your x, that's how far the airplane flew. And how fast is the distance y from Jim to the airplane changing? So they want us to find dy dt. So to do this, you take your equation and you take the derivative like normal. So derivative of 4,500 squared would just be 0. Derivative of x squared is 2x, but you have to tack on dx dt because x is some function of t. And derivative of y squared would be 2y, but also dy dt. Now you plug in all those numbers that you know and see what you get to. So 2 times 13,000 for x times dx dt, which is 400, equals 2 times y. I don't actually know y, so let's leave that blank for a minute. And I'm going to solve for dy dt since it's not actually by itself yet. So it's going to be 2 times 13,000 times 400, 5,200,000 over y. Okay, so if I just rearrange that equation, this is what I get. I don't actually know what y is though, but I could probably figure it out. Because up here I have 4,500 squared plus x squared equals y squared, and I know what x is. So let's come back down here and do an intermediate step of solve for y. So 4,500 squared plus x squared equals y squared, or 4,500 squared plus 13,000 squared, because we know that's x, equals y squared. So y should equal 13,757. Now let's plug that in up there. So this is going to equal 5,200, or 52 million, 5,200,000 over 13,757, which is 378. And this would again be feet per second. So let's see. So our airplane's flying 400 feet per second up here, so our actual distance here is changing at a rate of 378 feet per second.